my very distinct pleasure to introduce Professor Devi Parikh. Debbie is an assistant professor in the School of Interactive Computing at Georgia Tech, and also a research scientist at Facebook AI Research. Her research interests include computer vision and AI in general, and visual recognition, and in particular, visual recognition problems. Her recent work involves exploring problems at the intersection of vision and language. Debbie has earned numerous awards, too numerous to name here, but one that really is quite interesting to me is that she was named in the Forbes list of the 20 incredible women advancing AI research. So congratulations for that. That was fantastic. So it's my great pleasure to introduce Professor Parikh.
Thank you for the introduction. I'm excited to be here, and let's just get started. So my background is in computer vision, and so I've been interested in problems that involve taking an image like this and recognizing where all the objects are, where are the people, what are they doing, is this an indoor scene, is it an outdoor scene, and so on. But more recently, I've been interested in trying to take this image understanding and translating it to natural language. So for example, for this image, try and produce a caption in a single sentence that describes this image, or maybe tell a short story about this image, or answer a question about this image, and someday maybe even hold a natural language dialogue or a conversation that's grounded in the content of this image. Right? And so I think this intersection where you're trying to take images, understand them automatically, translate them into natural language, and communicate them in a way that's human-like, that often might require some common sense reasoning. I think this intersection is an exciting space. And let me try and motivate a little bit why this intersection of vision and language is interesting. And so the first motivation is that visual content is all around us. That's sort of vision is our primary sensor, and language is how we communicate, right? So if we have a way of connecting vision to language, this can enable many different applications, right? So things like if you're trying to interact with, organize, or navigate through large quantities of typically unstructured visual data, then having a bridge to language gives you a very natural way of doing this interaction, so you can look for whatever it is that you're searching for example. A lot of the content on the web is inherently multimodal. There's often text that goes with images or videos, and so if you have a way of connecting those two, you can take better advantage of all the information that's out there to just learn more about the world. If you think of applications that involve visually impaired users, where they don't have access to the visual content, but they still have access to the language, and so if you have a way of connecting vision to language, they can access this visual content through the language interface. And even if a user is not sort of biologically impaired, but is situationally impaired in the sense that there's just a very large amount of data that they have to sift through to look for what they're looking for, again, having a language interface to be able to access this content, which otherwise wouldn't be easily accessible, can be quite useful. Right? So that's one application, that's one motivation, the applications. Another motivation, more from an AI perspective, is that connecting vision and language gives us a way of demonstrating certain AI capabilities and measuring and benchmarking certain AI capabilities. Right? So for example, if I can take an image and if I have a system that can convincingly describe it in a single sentence, that's one way of demonstrating that I have a system that understands what's going on in the image. Right? Or the flip might also be true. If I can take a sentence and ground all the words and phrases from that sentence into some visual content, then that's one way of demonstrating that I have a system that understands what the language is talking about. And the third motivation is coming more from a computer vision perspective, where a lot of classical problems in computer vision, whether it's image classification or object detection or image segmentation, often involve taking images or bounding boxes or pixels and placing them into one of several different categories, right? For object detection, there might be 80 categories. For segmentation, there might be 20. For image classification, there's 1,000 different buckets. And so there's been a lot of work that's gotten good at taking these entities and putting them in one of several different buckets. But what happens when you try and connect vision to language is that because language is rich and compositional, you can't afford to have a bucket for every single output language that you might want, for every single caption that I might want to emit. right? So for example, I may have never during training seen thousands of examples that depict a steam engine is coming out of a fireplace, right? That it's unlikely that you've seen something like that. But at test time, if I see an image that is depicting that, we would expect our systems to be able to describe it, right? We would expect our systems to be able to compose the various objects that they recognize and the interactions that they recognize and produce a sentence like this, even though it's not one of the buckets that we've seen during training. And so looking at problems at the intersection of vision and language forces us out of this bucketed recognition paradigm, which can be quite exciting as far as modeling challenges go. All right, so those are the reasons why I think this intersection is exciting. And I'm going to start by talking about one specific problem that falls at this intersection, particularly of pictures and words, and that's visual question answering. Right, so visual question answering, the task is you're given an image and you're given a free form natural language question about this image, and we're trying to build AI systems that can answer this question accurately, right? So this is a visual question answering demo. It's online. It's hosted off of Cloud CV, which is a project out of Dhruv Batra's lab. And what you can do is you can upload any image, and you can ask questions about it. So things like, what is in this image? And it says food. What kind of food is it? Sandwich. Oops. How many sandwiches are there? 2. What are the sandwiches on plate? What color is the plate? White. Is there any wine in the image? Yes. What color is the wine? Red. Is there a fork in the image? Yes. Is there a spoon in the image? No, and so on, right? So the idea is you can ask any question about any image, and you expect to get reasonable responses back. And so visual question answering. Given an image, we're asking a natural language question, and we expect these systems to be able to answer them. And so what's interesting about this problem is because the questions can be asking about anything in the image, it could involve having to recognize small objects like what color are our eyes and recognizing the attributes, what is the mustache made of, recognizing objects out of context, is the person expecting company, where you have to recognize some social context, how many slices of pizza are there, involves counting, is this a vegetarian pizza, requires access to some external knowledge that says if you detect meat then it's probably not a vegetarian pizza, does it appear to be rainy, which is scene level attributes, and so on. So a lot of sort of classical computer vision problems and more nicely fall under the umbrella of visual question answering. And so what's interesting about this is it makes scene understanding task driven, right? You're trying to process and understand this image for the purpose of answering a specific question about it, and you don't know what this question is going to be till you're in test time, right? So only at test time do you know the task for which you're trying to understand this image, and so that's nice. And so one of the first things that we did to try and attack this problem is to collect a large data set. And so we collect a data set that has over 250,000 images like the ones you see here. These are sort of realistic consumer photos. And we've also collected this data set on 50,000 abstract scenes, which are these sort of cartoon images that you see here. And what's interesting about this is that the low level vision processing has already been solved. You know exactly where all the objects are. And so if you want to focus only on the higher level reasoning required to answer these questions, then this could be an interesting playground. And so for each one of these images, we collected 3 questions. So there's over 750,000 questions. And the way we collected these questions is we went to Amazon Mechanical Turk, and we asked people, we showed them an image, and we asked them to ask a question about this image that they think would stump a smart robot, right? And so this was an attempt at trying to get somewhat interesting questions going. And then we collected multiple ground truth answers for every question image pair, and so the data set has about 10 million answers in it. And this is all publicly available open source for people to use. So some interesting things that happen when you collect data at the scale on Mechanical Turk. So here's what one worker had to say who had done a lot of our tasks. Beware also the lasting effects of doing too many. For hours after the fact, you will not be able to look at any photo without automatically generating a mundane question for it. If I were in possession of state secrets, they could be immediately tortured out of me with the threat of being shown images of skateboards, trains, Indian food, and beep, giraffes. There are a lot of giraffe images in this data set. Please, I will tell you everything, just no more giraffes. The workers actually enjoyed these tasks quite a bit. They really liked doing this. This was just one amusing worker who had written to us, so I thought I'd share that. But so here's a visualization of what this data set contains, the kinds of questions that are in here. And so 41% of the questions start with what, 26% with is, 11% with how. And so you can sort of go around and look for n-grams and see at the top left what percentage of the data set falls within those n-grams. And then you can look at longer n-grams, like what is the man, and about 1% of the questions start with what is the man. And on the right, you're seeing the top most frequent answers to questions that start with that n-gram. So what is the color of? You will see a lot of colors to the side, what color is, and again, you see colors to the side. So this is just a nice way of browsing through to get a sense for what this data set contains. So that's what the questions. As far as answers go, about 38% of the answers tend to be yes or no. So 38% of the questions are binary questions. And 99% of the questions have answers that are less than equal to 3 words long. And so what's nice about this is that this makes evaluation feasible, because sort of natural language generation, whether it's visually grounded in an image or not, is just hard to evaluate. And so if these answers are shorter, we can get away without trying to evaluate natural language. But just because the answers are short doesn't mean this problem is easy. There are 23,000 unique one-word answers in this data set, which the model would have to deal with if it were trying to sort of attack the full spectrum of this problem. This is a visualization of the answers for different question types. So for example, if the question starts with the word are, then that tends to be a binary question where most answers are yes or no. Same thing with does or do, and then or is this. And then for questions like how many, as you might expect, you see a lot of number answers. For what color, you see a lot of color answers. But then questions like what is, what kind, what are, what type, there's just a wide variety of answers that this data set has that these models would have to learn to predict. As far as evaluation goes, we have 2 different formats. One is an open answer format where the input is just a question and an image, and the machine has to produce an answer. And then we also have a multiple choice format where you're given as input an image and a question and 18 answer options, and the machine has to pick one of those as the correct answer. And the way these options are constructed is we have obviously one of the 18 is the right answer. We have some just random answers from the data set thrown in. Those are usually easy to eliminate. We also add in the popular answers, so the top 10 most frequent answers across the data set. So those are hard to eliminate because statistics are going to be in their favor. And then the hardest and maybe the most interesting one are these plausible answers. These are answer options that are plausible but likely incorrect. And the way we collect these is we show people the question but not the image, and we ask them to answer the question. So for example, what is he playing? And so people are going to name generic things that one could be playing. So for example, guitar, drums, or baseball. But then if you look at the image, you realize that, oh, the person is playing tennis. Right? And so these are all options that are going to be added to those 18 options, which just based on the language you can't eliminate because they respect the language, they make sense with respect to language, and the machine will really have to look at the image to eliminate these as options to identify the right answer. And the way we evaluate accuracies is we say that, so we've collected 10 ground truth answers for every question from 10 different people. And we say that if a machine matches at least 3 of these 10 answers, then we give it 100% credit. We say that if you say the same thing as 3 other humans did, then that's good enough. And anything less than that, there's partial credit for it. And the reason we are not trying to get it to match all 10 is because there's interhuman disagreement, right? So for this question, for example, some people answered it by spelling television out, some people just answered it by saying TV, and we think that if the model says either one, that's good enough. All right, and so talking about interhuman agreement or human accuracy, here are some numbers. There's probably too many for you to take in all at once, but these are accuracies on real images, on abstract scenes, on all the questions, on just the binary questions, on questions that have numbers as answers. So a lot of the counting questions like how many fall under that, and then everything else. And I want to draw our attention to a couple of different trends. One is this is the accuracy of humans at answering these questions just based on the question. They're not even looking at the image. And that's about 40%, right? And so examples are, for example, what color is the banana? You don't have to look at it. You might guess yellow, and you're probably right in a lot of cases, right? And so this is capturing that. Here's another interesting comparison. If we show people the question and a caption for the image, but not the image, then this is their accuracy. But if we show people the question and the image, then their accuracy is much higher, right? And so this tells you that these questions are getting to details of the image that captions don't tend to capture. And so visual question answering is a more detailed, more fine-grained task than image captioning, for example. And finally, if you had to just take sort of one number to remember from this slide, then interhuman agreement on this data set is about 83%. So that, in some sense, is the upper bound that we might expect to get from machines in this case. All right, so let me talk about one sort of baseline model, which was one of the first models we looked at. It's what you might expect. The input is an image and a question. The output is an answer. We process the image with a convolutional neural network. We process the question with an LSTM, which is a kind of recurrent neural network. And then the output space is 1,000 different answers, which were the 1,000 most popular answers in this data set, right? And so just to walk you through that a little bit more, here's the CNN that's processing the image. Here's the LSTM that's processing the question. We transform the CNN representation with a fully connected layer to 1024 dimensional representation that you see here. We do the same thing with the question. We take a pointwise multiplication of these two to combine the two modalities, followed by a fully connected layer, and then a softmax over these 1,000 different answers, right? And so given an image and a question, you can get an answer out. And then you can look at some ablations of this, that if you weren't looking at the image just based on the question, how well would this model do? Or if you weren't listening to the question just based on the image, how well would this model do? And here are a whole bunch of comparisons. Again, it's too much to take in from a slide, but the main thing to take home here is that if you look at the question alone, the machine gets 50%, and then if it looks at the image, it gets to about 58%, right? And so this is sort of the baseline first model that you would think of. The image is playing a role, so that's a good thing. All right, so we were interested in trying to sort of analyze this data set. There are so many questions, they're all open-ended. We wanted to get a sense for which of these questions are difficult, which ones are easy. And so we thought of doing was, we went to Mechanical Turk and we showed them an image and a question. And to get a sense for how hard the question is, we asked people to assess how old they think someone needs to be able to answer this question correctly. With the idea being that if they think a toddler can answer this question, maybe it's an easy question, and if you need to be much older, then maybe it's a harder question. And so here are some examples of what people said. These are some of the easier ones. Is there a bird in the sky? What color is the shoe? And then here are ones where people thought someone needs to be older, like what type of architecture is this? How many calories are in the pizza? And so on. And so you can do some interesting things, that you can sort question types based on the average age that people have annotated. And so as you might expect, some of the simpler ones like what color, what animal, how many are towards the bottom of this list, and questions like what brand or why is at the top of the list. And so one thing I want to stress is that I wouldn't take these absolute age numbers to mean much, because these are untrained Mechanical Turk workers in uncontrolled environments. Just saying how old they think someone needs to be to answer the question, it doesn't mean someone actually needs to be that old. But this ranking, I think, is still meaningful, where you tend to see the easier questions at the bottom and the harder questions at the top. But then, and I know, like I said, these numbers don't necessarily mean anything, but once you have these annotations, it's tempting to try and put an age to the model. Like we can take that baseline model I showed you, check the age that people annotated for the questions that the model got right, and you can average that number, and in this case, it turns out that that number tends to be about 5. And if you look at the average age across questions, then that's about 9. And again, I would take these age estimates with a huge grain of salt, because these are, like, I'm not claiming that that baseline VQA model is as smart as a 5-year-old, right? That's absolutely not the statement that I'm making. Just that, like I said, the ranking gives you an interesting signal to keep in mind. All right, and so this space of visual question answering has been very exciting. We've seen a lot of papers from academia, industry, startups, oral sessions at CVPR, which is sort of our premier computer vision conference, have multiple papers on VQA. We've been organizing a challenge in visual question answering for 3 years now. The last one actually just ended a couple of days ago. We typically have about 30 teams that participate. And the current state of the art, at least up until a few days ago, was at about 71.5%. Right? And so I showed you that baseline model at 58. And so this is how much progress that has been made in about 3 years. And so I just want to give you a flavor for one of the more state-of-the-art models. This was state-of-the-art about a year and a half ago, so it's not the latest, but it's more advanced than the baseline that I showed you. And that is this hierarchical co-attention model, where by co-attention, what this model does is it reasons about which regions in the image are relevant to a particular question, and it focuses on those regions to answer the question, and it also tries to reason about which words and phrases in the question are important and tries to focus on those while answering the question. And the hierarchical part is coming from the fact that it models the question at multiple levels in the hierarchy, at the word level, phrase level, and entire question level. And so let me spell that out a little bit more. So here's an image, here's a question. We're going to reason about the question at the word level. So there's an embedding that captures each word in the question. And then we have these little convolutional neural networks, convolution layer with max pooling on top, that each timestamp decides how wide of a window it wants to look at. So in this case, for the first timestamp, it decides it wants to look at the 2 words. At this timestamp, it decides it wants to look at 3 words. And then at every other timestamp, it just represents a phrase as the individual words at those timestamps. And then at the highest level, we have an embedding for the whole question with an LSTM. And then for each one of these levels in the hierarchy, the model reasons about which regions in the image are relevant. So that's where you see this heat map, that's an attention map on the image, and a heat map over the question that tells you which words and which timestamps are important. And the same thing at the phrase level, same thing at the full question level, and all of this information is recursively combined for it to then spit out an answer to this question. Right? And so this model, for example, gets at about 66% accuracy. So it's kind of halfway between the baseline that I showed you and the 72% that we have now. So even at the 71.5 or 72% accuracies, there's still a lot of things that these models can't do well. So for example, if there was an image like this and a question that said, how many vegetarian slices are left in the pizza box, I would be very surprised if any VQA model today got this right, and certainly not for the right reasons. Even if it gets it right, it would probably be by fluke. And there's several reasons why it can't handle this. One is these models don't have explicit counting mechanisms, right? It just has this output softmax layer over 1,000 different answers, and numbers like 1, 2, and 3 are just some class ID. It doesn't know that the number 3 is closer to the number 2 than it is to 1, right? So there's no explicit counting mechanism. It doesn't have access to external knowledge bases. So the fact that vegetarian means there should be no meat on the food, that's not something that these models have access to. It can't reason. So things like how many slices are left means how many slices were there to begin with, and minus how many slices are gone. That sort of multi-hop reasoning is not something that these models can do. It doesn't leverage compositionality. So even if it has seen pizza slices during training, if it has seen other vegetarian food during training, it doesn't have a mechanism to put those together and realize what vegetarian slices look like. Right? It would have to have seen examples of vegetarian slices in particular during training to be able to generalize that to test time. And it lacks consistency. So if I ask it how many slices are left in the box, how many slices were there to begin with, and how many slices have been eaten, those numbers aren't necessarily going to add up. Right? And so just to give you a quick overview of many of the other things we've done in this VQA space, we have a second version of the data set that is much more balanced in terms of the language priors. So for every question, we now have 2 images that are quite similar to each other, but have different answers to the same question. So this makes the problem harder, and the models really need to ground their reasoning in the image. We've looked at counting specifically to see if we can get these models to count better. We've looked at visual question answering as giving you multiple perspectives for the same image. So when you ask it different questions about the same image, you're extracting different information from that image. And so you can think of that as a feature representation that you can use for other different but related tasks like image captioning, and we found that that works quite well. We've looked at trying to get these models to be more human-like. So if you ask them irrelevant questions like what color is the cat when there is no cat in the image, right now the model will just go ahead and answer the question with white or black or something like that. But we've tried to see if these models can respond by saying, no, there is no cat, this question doesn't make sense. And everything that I talked about was just one round of interaction, right? Just one question, one answer, and then you move on. And so we've looked at trying to extend this to visual dialogue and visual conversation. And so let me just show you a quick teaser for that, where we've collected this data set, where we paired two people on Mechanical Turk. One side is the questioner, they don't see the image. The other side is the answerer, they see the image. They talk to each other through this live chat interface, where the questioner is asking questions, the answerer is answering questions, and it's an actual conversation that's going back and forth. And so we've made this interface to collect the dialogue data set publicly available. And we've made the data set available that has 120,000 images, 1 dialogue per image, 10 rounds of question answering for every image. That's a total 1.2 million dialogue rounds that if you're interested in this space, you're welcome to check out. All right, and so we trained some models for this, and here's sort of a visual chatbot that we've built around it. You can upload an image. It starts by describing it, a large building with a clock tower in the middle. Where is this? Looks like a city. Are there other buildings? Yes. Are they tall? Yes. Great. How's the weather? Cloudy. Anything else? There is a building in the background, but I can't tell what it is. Right? And so you're seeing these longer responses from the bot as opposed to short one-word answers, because this is trained on dialogue data where people were having a conversation, and so the strings tend to be longer. We've also been pushing this from just vision and language to vision and language and action, where we now have virtual agents embedded in an environment like this home. So here an agent has been spawned at this location in this virtual home. You ask it the question, what color is the car? And so the agent has to navigate through this space, get out of this doorway. So it's trying to look for the car so it can figure out what color the car is. And so it's trying to get out of the doorway. It's going to look around for the car. It spots the car, and then it can answer the question with orange, right? And so this is embodied question answering, where the agent is doing active perception for the purpose of answering a question that you've posted. And so if anyone's interested in this, I can talk to you more about this offline. One thing that I want to mention before I sort of switch gears and talk about common sense reasoning is that a lot of this work that I talked about has natural language at its core, right? And one reason why we want it to be natural language is because we expect these systems to be interacting with humans, right? Otherwise, there's no need for the language to be natural or interpretable to a human. And so we've been doing some work on trying to focus on this aspect of human AI teams, with the idea being that as AI gets better, humans and AI are going to be working together as teams trying to accomplish certain common goals of interest. And a lot of times when we think about these teams, we place the emphasis on the AI to build a mental model for what the human is thinking, what their intentions are, what their strengths and weaknesses are. And we think that for this team to be effective, that is certainly important, but it's also important for the human to have a mental model of the AI, to have a sense for what it's good at, what it's bad at, when can it be trusted, when is it likely to fail, and so on. And so we've been doing this work towards what we're calling the theory of AI's mind. It's perhaps a little bold of a title there, but we're trying to see if we can get humans to predict when the AI is going to succeed and when it's going to fail and what its actual response is going to be. And it's interesting because in the case when the AI is the neural network, this is a human now trying to mimic or approximate a neural network instead of the other way around, which is what we're used to thinking about. We've evaluated whether these different explanation or interpretability modalities that are out there, do they help humans build this theory of AI's mind more accurately, which we've put these human and AI teams together for certain common tasks like cooperative games. And all of this for now we've done within the scope of visual question answering. So if you're interested to know more about this, I'm happy to talk to you about that. All right, so I want to make sure, how much more time do I have? Is that accurate? I have 20 minutes. Okay, great. And so the next part of the talk that I want to talk about gets into some common sense reasoning. And the idea is the following, that if you look at sort of state-of-the-art image captioning models, they do a pretty good job at describing images, right? For this image, we have models that can say a man in blue wetsuit is surfing on wave, or a group of young people playing a game of frisbee, a car is parked in the middle of nowhere. That middle of nowhere is interesting that it picks up on that. A pot of broccoli on a stove, right? So these are descriptions where it recognizes objects, some interactions, and strings it together in a coherent sentence, and so this sounds great. But if you think about what it would take to describe an image that looks like this, right? Like you and I might say, a man is rescued from a truck that is hanging dangerously from a bridge, right? Now these models are probably going to be fine at detecting the truck and the bridge and the man, but if you think about what it takes to use words like rescued and dangerously, it takes much more than that, right? It takes more than just the pixels in this image. It takes a whole bunch of world knowledge and to get a sense for what people's intentions are, what they're trying to do, what must have just happened before the scene, what is likely to happen just after, and all of that needs to come together for you to say something like rescued or dangerous. And that is just completely lacking from all the models right now. right? And so what we're trying to study is how can we learn this world knowledge or common sense, if you will. And so one source that people often use is text. There's a lot of text on the web, and we can try and learn world knowledge from that. But that tends to be problematic because text is known to have reporting bias, right? Humans generate text for the purpose of communicating with other humans, and there isn't usually a need to communicate mundane, low-level common sense knowledge, and so we don't talk about that in text, right? We like talking about interesting things, which doesn't let you learn common sense. And so here's an example of that. This is how often these different phenomena are mentioned with respect to people in a large corpora of text. And if you were to interpret these frequencies of mentions to correspond to frequencies of them happening in the world, you would draw some strange conclusions. So for example, you would conclude that people inhale 6 times as often as they exhale. Or maybe even worse, people get murdered 17 times as often as they exhale. Right? And that's not the case. It's just that if someone were to get murdered, unfortunately, that's what we would talk about. We wouldn't talk about the exhaling. Here's another example. This is how often different body parts get mentioned. And you would conclude that people have heads 1,100 times as often as they have gallbladders. That's not the case. It's just that for whatever reason, we don't like talking about gallbladders, and so they don't get mentioned in text too much. So text is a useful source, but it has its issues. And so our thought was, well, maybe if we learn common sense or world knowledge from the visual world around us, it sort of is what it is, and maybe that will have less of a reporting bias or at least more complementary signals to text alone. And there is a lot of sort of rich semantic structure to our scenes, right? If you look at this image and if you had to describe it, you might say these are 2 professors conversing in front of a blackboard. And now if I change just one subtle scene about this image, your description might change, right? You might say that these are 2 professors standing in front of a blackboard as opposed to conversing in front of a blackboard. And so the fact that the subtle cue of gaze can change the interaction between 2 people, that is something we would hope to be able to learn from the visual world, right? But the problem is that we don't have access to visual data that is sort of dense and rich in this sense. It's hard to find 2 images that differ from each other in these subtle ways, in subtle but meaningful ways. Right? And so our thought was, well, do we have to restrict ourselves to real visual data? Can we use non-photorealistic data to learn this common sense? Because the common sense doesn't lie in the low-level RGB pixel values. It lies in the semantics of the scene, and the semantics of the scene can still be fairly rich even if it's not photorealistic. Right? So that's where we were headed. That's what we wanted to test. And so for that, we introduced these 2 characters, Mike and Jenny. And they had this world of sort of different outdoor objects, different trees, different weather conditions, different animals, different toys and foods and beverages that they can interact with. Mike and Jenny can have different expressions, different poses, and you can put together this sort of fairly straightforward interface, drag and drop interface, where people can drag and drop these different objects, sort of change the scale a little bit, flip them around, and fairly quickly you can get this nice rich scene, right? If I had to ask you to describe the scene in a paragraph, that wouldn't feel very unnatural to you, right? The semantics are quite rich. And once you have this interface, you can do interesting things. I can show you a sentence like Mike fights off a bear by giving him a hot dog while Jenny runs away. And I can ask each one of you in this room to create a scene corresponding to this using the interface that I showed you. And each one of you will probably create different instantiations of what this looks like, right? Some of them may have trees, they may not have trees. Even if they have trees, they might be different kinds of trees. There may or may not be clouds or the sun. Where exactly Mike and Jenny and the bear are will change. Which way they're facing might change. But what's consistent in all of these is they all have Mike facing the bear, holding a hot dog, Jenny in a running pose facing the other way, right? And so now we can reason across these scenes to get a sense for what is it about these images that captures the meaning that was central to the sentence that was given. And if you were to try and do this with real images, that would be very difficult. You wouldn't be able to find 10s or 50 different examples of real images that are all different but correspond to the same meaning. Right? And so you can learn this from abstract scenes. Here's another example. We wanted to learn what it looks like for different people to be interacting with each other, like one person holding hands with another person, walking with another person, talking to another person, arguing with another person. And so you could drag and drop these people. In this case, you can also move their poses in fine-grained ways. You can change their genders. Here, someone is depicting one person dancing with another person. For a while, it kind of looks like a person is hitting the other person. But if you just give it a second, as soon as the expressions change, the meaning of the scene changes, right? And this is something that, again, now for each interaction, we can get multiple people to create what these interactions would look like. And you get fairly detailed poses here. Like, so for dancing with, I was surprised by the variety of poses that these Turkers created. And you can now learn from this data what these interactions look like. And we've done some experiments to show that it can generalize to real data as well. All right, so coming back to common sense, the things that we're going to look at are going to be text-based tasks. So the input is text. There's going to be some common sense reasoning that the model needs to do. And the key idea is going to be that when you're given this text, instead of just reasoning about the text alone, you should imagine the scene behind this text and also reason about that scene and reason about the text and the imagined scene jointly. And the idea is that you will be able to solve the task better than if you reasoned about the text alone, all right? And so let me give you an example of this. So if the task is given two descriptions, do they describe the same, are they describing the same scene or not? So Jenny was going to throw her pie at Mike. Jenny's very angry, she's holding a pie. And now you could sort of in text reason that if someone is angry, they might be throwing something, and to throw something you have to be holding it. So these two descriptions could be talking about the same thing. But our idea was that, well, if I instead just imagined someone throwing something, I will also imagine them holding it. And so in this visual space, it will be much easier for me to reason about the similarities of these descriptions than it is on the surface of the text alone, right? So here's another fill in the blank question. And the way we're going to solve this is that we're going to plug in each option into this description. For that description, we'll generate a scene. We'll do this for all 4 descriptions. And then we'll reason about both the description and the text. And the idea again is that about the image and the text. And the idea is that these imagined scenes need not be photorealistic, because that's not what's central to common sense reasoning. And so we'll imagine them in this clip art world, right? And so we'll given a description, we're going to generate these images in this clip art space. We can process the description to extract certain tuples, and then condition on the tuples, we use a CRF model that reasons about which objects are present, where they are, what attributes they have, to then generate these synthetic images that you see on the right. And we can train a model that says, given a question and the correct option plugged in and the corresponding scene that was generated, that should score higher than for that same question if the incorrect option is plugged in and the scene that you would generate. And in this case, we trained this with a ranking SVM. And what we find is that reasoning about the vision helps over the text alone. We've also done some follow-up work on, instead of explicitly generating these scenes and then reasoning about them at test time, just sort of learning word embeddings that are already informed by the visual interpretation. So visual word to vec that already captures this visual information in the embedding. So at test time, you don't need to reason about the explicit scene. All right, and so we've done quite a bit of work in the space of trying to use visual abstraction for a variety of problems like connecting images and language, for zero-shot learning, like learning what it looks like for 2 people to interact with each other without any real examples, just from interactions. We've studied phenomena like which image tends to be more memorable to people, which image tends to be very specific, where everyone describes it in exactly the same way. And we've also studied visual humor. So for example, we had Mechanical Turk workers create funny scenes for us. In some cases, I couldn't always tell why they thought the scene was funny, so I would ask them why they think it's funny, and they'd say things like, this terrified woman's home is being invaded by mice as the cat sleeps. Or in this case, the man is about to trip on his child's car and spill wine on his wife. They thought that was funny. I personally wouldn't find that very funny. But so we've studied what makes a scene funny, how you can make it funnier, how you can make it less funny. And all of this is easy to study in this abstract world where you can vary the distribution of the visual content that you're looking at. And so sort of studying these high-level image understanding tasks without having to be bogged down by sort of the low-level vision. And I think what's nice about this is it's a very rich annotation modality, right? I can show you a scene and ask you to describe it. I can also do that with real images, but now I can show you a description and ask you to depict what that looks like visually. That's something that's hard to do with real images. I can show you a scene and ask you to modify it in a way that the meaning changes, or I can perturb a scene and ask you how the meaning changed and so on. So sort of it opens up this regime of trying to learn by playing in this abstract visual world, which I think can be very exciting. So I think overall there's several open directions along the things that I've talked about. One is active learning. So for visual question answering, sort of questions and answers are a very natural modality. So far we're asking the machine a question, but it's tempting to flip that around. So the machine can be asking us questions to learn more about the world that it doesn't know. And sort of if you bring in the learning by playing aspect, then this can be a very rich interaction to extract information about the world. The whole space of access to external knowledge base and common sense reasoning is completely lacking for the most part in many of these models. Complex reasoning is lacking, and so I think bringing all of that in will be necessary to get to sort of human level consistency in tasks like visually grounded dialogue, so these agents feel like we're interacting with a human. And so just to summarize, I've talked about quite a bit, I think a little too much, in the spectrum of vision and language. So there was work on image captioning. We made that active to visual question answering all the way to visual dialogue, which is sort of going back and forth. The space of vision and language and action. So I will show you a very quick teaser on embodied question answering, where an agent is navigating in a virtual world to answer a particular question. I think that space is exciting. Common sense reasoning is a space that I think has a lot of work that can still be done. Interpretable AI and human AI teams, I think is also an important direction that is sort of on the periphery of many of the things that I talked about. This is my lab, so these are all the amazing students that have done a lot of the work that I showed you. A lot of the work that I do is in collaboration with Dhruv Batra's lab that you see here. These are all the external collaborators that have been involved in this work. And so with that, with still 10 minutes remaining, I will stop. Thank you.
Thank you very much, Devi, for a wonderful talk. There are 2 mics in the hall, and if you have questions, please line up for questions. In the meantime, I was really quite surprised that earlier in the talk you said that the interhuman agreement was 83%. That was quite an interesting finding, I find. I'm sure they weren't engineers. It would have been much lower.
Right. Yeah, I mean, some of it comes from the fact that people might just say different things, like television versus TV, and so you're not going to get 100% agreement on that. Things like what color is something, someone might say off-white, someone might say beige. We had these debates and conversations all the time, what's off-white versus beige, so there's going to be disagreement there. In some cases, if someone is saying, oh, is this a shiny surface, someone might think yes, someone might think no, someone might say maybe, and so there's disagreements there. And so the thing to keep in mind is that this interhuman agreement is being computed with exact string matching, right? So if 2 people say the exact same string, that's when they're going to match, otherwise they're not. And so I think that's sort of what explains why it's at 83%. Or were you saying it's too high?
Well, if there were engineers, it would be 50.
Right.
Okay, we have somebody here.
Hi, that was a wonderful presentation. Thank you.
Thank you.
So if I was at a campground and I saw a bear behind me, I'd want to know if it was going to attack me. Is the current state of the algorithms that you have been working on, would it be able to make that inference that there's a bear, because it's a bear, it might be a violent animal, and it might attack the children? And what level of complexity of a scene can you anticipate, I guess, because it's sort of an anticipatory cognitive action.
Right. And so I think that's a great question. There is quite a bit of work that's going on in sort of these predictive models that are trying to predict what's going to happen in the future. Most of these works tend to try and predict the next scene in terms of the pixel space. So if I've been watching a video for a few seconds, I'm trying to predict what the next frame might look like. So there's some work that tries to predict the physics, that if I drop a ball, if there's a picture that shows me holding a ball here, and if you have to predict what's going to happen next, then the model is expected to sort of draw an arrow in the direction in which the ball is going to go. So there's things like that. As far as I know, there isn't a lot of work that is predicting the semantics of the future, things like the bear is about to attack me, or these are properties of the scene that are going to change. Most of the work that I've seen either predicts in the pixel space or some very basic physics like arrows of motion and things like that. But that is very much a space that everyone is interested in. Also for unsupervised learning, because if you're just going to predict the future, then to get a supervisory signal back, you just need to see what happens in the future, right? And you can get that for free if you have things like videos, and you don't need human annotations. It's also a very rich source. It's a task that doesn't need human intervention for supervision, at least when posed as future prediction. And so that's attractive.
Any other questions? Yes, there's another question.
Hi, what I found fascinating was when you asked folks to rank what age would a person be or a child be to answer this correctly. And it wasn't too long ago when you would say vision is about as smart as a baby or a 1-year-old or a 2-year-old. So now the median's definitely shifted to be older, right? So the question I would have there is, the other fascinating piece I found was the dialogue where the AI is asking questions back and learning from it, much as a child would, right? So the question there is that interactive, or are we there yet? Or is that something that is going to be happening soon? Where is that going? Is it something which is incremental and builds upon itself in semi-real time, or is it something that's offline?
Right. So I think about your first point, though, like I was saying a few times, there's a huge caveat there, right? I would not trust those numbers to mean the actual age. So when I say that VQ model was, I think it was 4.75, that is not to say that the VQ model is as good as a 5-year-old would be at processing even the word. So these are untrained mechanical Turk workers making these assessments. I think those absolute numbers don't mean anything. So I wouldn't read too much into that. In terms of the interactive learning with the machine asking a human questions, that is something that people are looking at. You're sort of starting to see papers at CVPR and other conferences in that space. It's not at all mature enough to actually see where Alexa or some sort of agent like that in your home will start asking you questions to learn more about your specific situation or anything like that. So I think it's very far from being something that we can actually deploy anytime soon. But there is work in the very researchy space of trying to see how we can do that. And the way the experiments tend to be conducted is still very much offline, where there is assumed to be some oracle that can answer every question that the machine can ask. And that's how they learn, because it takes many, many interactions before the model gets better. And so actually running this online with a human in the loop would be too expensive right now till these models get better.
Thank you.
Yeah, really good presentation. To what level does your research use like semantic reasoning engines to like expand the universe of knowledge that you have about semantics, or are you really constrained to what the Turkers are saying the words and concepts are?
Yeah, we very much right now are constrained by what the Turkers are saying. There is a lot of interest, and that's why I brought it up multiple times in my talk. There is a lot of interest in trying to find robust ways of taking advantage of external knowledge bases, whatever source they may be, whether it's sort of very structured knowledge base or just Wikipedia text that's out there in unstructured forms. There is very initial work on things like memory networks, where they start with some bank of knowledge that's been represented as embeddings, and then this neural network learns which facts to query for which input and learns how to reason over them to then solve whatever the task is. So I think those architectures make sense, but so far they've been demonstrated in fairly toyish and contrived settings, and not sort of at larger scales like the kind VQA would need, and not with large open-ended knowledge bases that are realistic. So there is a lot of interest there, but I don't think anybody in the community has quite figured out how to get it to work well.
Thanks.
Any other questions?
How fast is this? Because I'm thinking of inverting the problem, which is like I have a corpus of pictures. Show me images of people in conversation. Like, does it? So I'd want to inverse it. So if you multiply by the corpus, then if it takes 1 second and you have 1 million images, I don't want to wait 1 million seconds for the answer.
Right, but I don't think it would quite end up being that. So if you were trying to do sort of image retrieval based on language queries, which is what this sounds right, that find like
right.
If the description is a person is having a conversation and you want to find all images that match that, you would be able to do that fairly fast, assuming your database of images has already been pre-processed, so you have embeddings
So you
saved for that.
pre-computed what's going on in every image.
Essentially,
Okay.
yes. If it was, which I think you would do for any retrieval setting, because it would probably be a static set of images from which you're trying to retrieve this. And right, or I don't know if you have a scenario in mind that's more streaming or online.
Right.
So yeah, and there is work on sort of language-based retrieval that works reasonably well and fast.
Right.
So, yeah.
But it's sort of, that assumes your system has asked all the questions a person would ask.
No. So I'm saying that only the vision side of it has been pre-processed. So just representations of what the images contain has been pre-processed and stored. But then whatever your query is going to be, you would be able to process that on the fly, because that's
okay.
just
So
one
if my
query.
million images, I can rule out anything that doesn't have people, and then I can say, which of these?
No,
have
you would have your whole database. You will have embeddings that already has information about whether there are people in it or not explicitly as that, but like the CNN representations will have that information. And then you have a test query that comes in. That is just one query that needs to be processed. And then the matching can be fairly fast, right? That's sort of like nearest neighbor matching. And so, yeah, you wouldn't need to know ahead of time everything that people would care about. You would just have to trust that your CNN or whatever other representations are robust enough
that
and
you have the
universal
NN
enough.
model built for every image.
Right.
Right, okay.
Yeah.
My question is that it seems you have two levels of intelligence, right? So you have the CNN for the visual, to pick up the visual details. You have another level of the language modeling, basically modeling the abstract concepts. So my question is that if your application seeing more and more things, more and more different situations, the CNN for to pick up the image details, will the network expanding or you switch to different things, switch the network ways or that something like that? How do you handle that?
Right. So what ends up happening is that eventually the CNN representation and the language representations are going to interact. Right. So in my case, the baseline model that I showed you, that interaction happened all the way at the end when the question had been processed, image had been processed, and then just the last two layers had the fusion. But that interaction can happen fairly early. And so if that interaction happens early, that is essentially the language affecting the visual processing of the image. And so if there is a different question, then the visual processing will be different because the fusion is happening earlier. So that's one way in which to adapt to the fact that based on what you're asking me, I'm going to process my image differently. These attention mechanisms also try and do that based on the question, they're focusing on different regions of the image. And so that's another way that's essentially changing the visual processing also. And of course, you can also make your CNN higher capacity and sort of have ensembles and all of those things that you could do that might also help.
But do you need to adjust the scale of the CNN, or it's just
You do
fixed?
need some normalization for the fusion, and that makes a big difference in this case. So the model that I showed you, if you normalize the image features, it works several percentages better than if you just let it unnormalized. And this is an issue that comes up anytime you're trying to fuse multiple modalities. So yeah, that's a valid point.
Thank you.
Any other questions? I do have a question.
Yeah.
So earlier you said that explicit counting is something that the models can't quite do today. So what is the state of the art? Where are we now?
So there is a couple of different groups that have looked at counting specifically. There isn't a large amount of work in that space.
There isn't.
There isn't. There is not.
Interesting.
And so one way of thinking of counting is that, oh, that's just detection. If I can detect all the objects accurately, then I can obviously count them. And that is true, but that becomes problematic when you have questions like how many men are wearing red shirts. Right? So these questions are not just how many people are there, how many cars are there, how many trucks are there. If those were the questions, then you could just run detectors and do it quite well.
Absolutely.
Object detection works
But the
reasonably
pizza
well.
example was a good example. It's like how many vegetable
Exactly.
pizza
So
slices are left.
Exactly. So one, it's unlikely that you have pizza slice detectors because how many things are you going to train detectors for?
Exactly.
And two, there are these attributes that modify it. And so you're not going to train a detector for vegetarian slices and pepperoni slices and mozzarella cheese slices and all of that, right? And so so you do have to deal with the richness and compositionality of language while trying to do this detection counting like task, and how to do that well is not clear yet.
And how, do you have a sense of how long it will take us to get to that level?
I'm not really sure. I'm not really
Yeah,
sure. I mean,
so-
detection has been going up very quickly in the last several years. And so much of that should also benefit counting tasks. But the richness of language and the fact that we still don't have vision and language models that ground themselves well in the image, I think that's an open problem that we
Right.
don't have good ideas for. And counting involves both of those. So the detection improving is going to help, but that's not the whole story.
Absolutely.
And so, yeah, I don't have a sense.
Yes, question here.
Hear me?
Yes.
How about synthesizing data, like in terms of training networks to synthesize the pictures, the representative pictures from the words, and then back and forth basically on that training data?
Right. So there is some work on, you're not talking about counting specifically, right? Just right. So yeah, so there is some work that tries to set the cycle up, that if you're trying to train image captioning models and you have these data sets of images and captions, then you start with an image, you go to the caption. From the caption, you try and generate the scene, and then you insist that this generated scene should match what the input scene was.
Yeah, so the
And so you
loss
get a
function is
cycle
basically
back. Exactly. And you can also do it the other way around, where caption to image to caption, and you insist that the caption matches. And they found some improvements in performance. Sort of realistic image generation is still a hard problem, especially at high resolutions with all the details of images like the ones I showed you, like these consumer photos on Flickr, like the Coco images. So that's still a hard problem, but some people have shown that setting up this cycle does help with performance.
Well, thank you very much for a wonderful talk, and thank you for showing us where the limits are of our knowledge. So this is fantastic. Thank you so much.
Thank you.